Okay, so recap of what we did yesterday. We learned the basics of how to quantize a free scalar in the Sitter space. We were motivated by the desire to perform a quantum field theory calculation that eventually predicts cosmological perturbations. And eventually we said the thing we want to compute after we quantize it are correlation functions that we had defined in this way. And the only correlation function we actually computed was the two-point function in the free theory. And we found that for the field of arbitrarily mass is always equal to just the mode function squared. And the mode function are given by Hankel function for fields of general mass. I cannot open my notes, unfortunately. Let's see if I can get through. And for the field, for a massless field, we found this formula, and we said that what we actually get to measure is the correlation functions at late times. And at late times, they are just a constant divided by k cube. That's a very characteristic result. I didn't comment on it last time. If you take this two-point function, it's slightly different from the two-point function in Minkowski, which is 1 over k. If you Fourier transform the two-point function in Minkowski, the Fourier transform is 1 over r squared, which represents the decay of a force mediated by a massless particle at large distance. While if you Fourier transform this in position space, this means that phi x and phi y, their correlation function does not decay with distance. It's the same correlation function at every distance. And so this is what people call scale invariant. So just free quantum field theory in the Sitter space generates a scale invariant two-point function that don't depend on distance. And as we will see, or as I mentioned last time, this is actually what's measured in the data, up to a 3% deviation. And we measure the primordial two-point function of this variable zeta that we introduced is exactly indeed is scale invariant. And so we are very happy that this result recovers that general scaling. Finally, what did we say last time? Oh, we introduced these diagrammatic rules. To compute correlators, and there are vertices and there are propagators, and we review all of them. And in principle, now given a concrete theory which specifies the interaction, you can do the calculation. As an example, we were working in Minkowski and did the simplest possible interaction, that is phi to the n, and we just blindly applied those rules, and we found the result, which was here. It was the coupling constant, because we computed two linear coordinates in the coupling constant divided by the product of the energy times the sum of the energies, this thing we call E total. Good, yeah, the rest was coming from the questions that we got. Are there some more questions today that you had the time to maybe review some of the things we did yesterday? Okay, no questions. Then I'll continue with another example. This is another calculation, but now this time we're going to actually do it in the Sitter spacetime. And for a reason that perhaps will become clear later, I'm going to consider the interaction Hamiltonian. Given by lambda over n factorial, but instead of phi to the n, I'm going to put phi dot to the n. The reason is that in the Sitter, because it's an expanding universe and the expansion is accelerated, there is an infinite amount of volume in the future, and the volume that is always increasing. And because of this, if there are some issues with divergences of time integrals at late times, but as long as we consider interactions with derivatives, redshift because of the expansion of the universe, and these divergences are absent. So to avoid technical complications to do with these divergences, we consider this interaction. I should also mention that these are the type of interactions that appear in realistic models of inflation. Good. So what is it that we want to compute here? We want to compute an endpoint function. The calculation is actually very, very similar to what we did last time. In principle, it's the sum of two diagrams. The second one is just the complex conjugate of the first one. So when you add them up, you get 2 times the real part of the first one. The first one is a left diagram, so it's minus I, sorry, a right diagram. This one, remember, this was the right, this interaction here was the right one. So minus I lambda, and then again there is an n factorial because I connect n legs divided by n factorial, that cancels out. I have to integrate this over all possible times. The integral is integral in dt, sorry, integral in d8 square root of g. That's the measure. What is square root of g? That is the determinant of the metric, which is a to the 4th. And recall in the sitter is a space where a is equal minus 1 over h eta, where eta is a conformal time. Last time we wrote a in normal time, which is e to the ht, but if you convert it to conformal time, is minus 1 over h eta. And therefore a to the 4th is 1 over h to the 4th eta to the 4th. Good. And then we have to write all of these time derivatives. Every time derivative should be contracted with a power of the metric. The time derivative has a time index down, so I have to contract with a time derivative up. And there are going to be n time derivatives, so the metric up will go to like n over 2. And then each one of the external legs should be this bulk to boundary propagator that I define, I call it GR. Each one of them depends on the external momentum and on the time that it is integrated over. And each one of them I should take a prime, where this prime, well, maybe let me just write it more explicitly. I should take the derivative of each one of them because I'm looking at a derivative interaction. And maybe to be clear for everyone, in my notation, a dot is d in dt and a prime is d in d eta. And d in dt is related to d in d eta by d in dt is h eta d in d eta, simply by changing coordinates. Good, so now I have everything I need to perform this integral to lambda, the real part, and now inside the integral is minus I collect all the powers of Hubble, and minus 4. I'm still left with this integral in the eta. The powers of eta is the number of derivatives minus 4. That's always the case. That's what ensures the scale invariance of the result. And then I collect all the mode functions. So let me specify this mode function to be those of massless particles, so I can copy them from what we had written before. Each one of them comes with the same normalization that we encounter, h over 2ka. And then I have to take the derivative of the mode function. So I have to do the d eta of 1 plus I k one minus I k eta e to the plus I k eta. I have to do that derivative. This derivative is simply ka square eta e to the I k eta. And so I can collect all of these factors together. Minus 2 lambda h to the 3n minus 4 divided by Notice that there are all the k square here and the k cube here, so I get just 1 over the product of all possible k's. And there is a factor of 2. And then I'm left with the real part of this integral, minus I integral in d eta from minus infinity to 0. Remember, minus infinity gets a little I epsilon, eta to 2n minus 4, because I had n powers of eta here, and I have n more here, so that's 2n minus 4. E to the I et eta, where now, just like before, I introduce this total energy to be the sum of all the k's. And I can perform this integral. I can give you the master integral to perform this. All these integrals can be performed using this. Well, basically, you see how you're going to do this integral. You're going to do integration by part from here to here until you get rid of all of these etas, and then it's just the integral I showed you before of e to the I eta, which is 1 over I. So that's the strategy. And when you do all of those integration by part, you collect some numerical factor. So the master integral is integral minus infinity. I already applied this I epsilon prescription that allows me to drop the boundary condition. So for any eta to the p, e to the I e eta, the result of the integral is I to the p minus 1, p factorial divided by e to the p plus 1 for every p bigger or equal to 0. So you can use this. Notice that we basically knew that this was going to be the result because just by dimensional analysis, this is of order eta to the p plus 1, so it should be 1 over e to the p plus 1. The factors of I and the numerical factor you can just keep track when taking the integration by part. So we finally obtain our second result, which is that in the sitter, this endpoint correlation function is some coupling constant h to the 3n minus 4. The product of all momenta, n of them, the total energy to the power 2n minus 3. And finally, there is minus to the n plus 1. If you keep the minus sign, there's a factor of 2. And then there is a 2n plus 2n minus 4 factorial. So that's the result of our calculation. So as you can see, now we just reduced the problem to a mechanical problem. For any model, we can turn the crank and compute more and more complicated results. This actually has been what people have been doing for the past maybe 20, 25 years. They've written down different models with different fields and different interactions. And for each one of them, they have been performing similar type of calculation to see what the correlators are. And finally, they have compared those predictions with cosmological data, the distribution of both galaxies and the microwave background temperature, to check if they see the signal. And so far, except for the 2-point function, they have not seen the signal, but they're still looking for it. I will not give you more examples, but you have understood how to use these rules, at least in principle, and then it's a matter of practicing it. What I want to do is that I want to show you a rather different way of performing the same calculation, which of course gives the same result. But that will introduce a new object that will be very interesting and important for us, which is the wave function. And that's actually the object that maybe at the end I will discuss briefly to give you a flavor of what more modern research is about. So let me introduce this idea of the wave function. And just to be very clear from the get-go, by wave function, I mean the same thing that you learned about the first time that you learned quantum mechanics. We have a Hilbert space of states. If we project that Hilbert space on a basis, or rather a continuum set of states, on that basis, we can describe that state as a wave function. For example, the wave function of the harmonic oscillator is e to the minus x squared. And because here we're doing field theory rather than quantum mechanics, this will be a wave functional, but I will still call it the wave function. Presumably, none of you have seen this in your quantum field theory course, and probably you will not see it. However, it is an alternative description of quantum field theory, perfectly valid, just like in quantum mechanics. And so I want to show you how to use it. So alternatively, instead of doing what we have been doing so far, we can use the Schrödinger picture. For quantum field theory, which is not what usually people do. Usually people use the Heisenberg picture, so they never evolve the state, but they evolve the operators. Well, we're going to evolve the state as we did when we learned quantum mechanics. Okay, so this wave function is the one that solves the Schrödinger equation. So to introduce it, well, we just say that the system is in some state, omega, and the state changes with time because we are in the Schrödinger picture. And the way it changes with time is with time evolution operator. So this is going to evolve it from some time. For example, for us will be from minus infinity to some time eta. And then, of course, it depends on some initial condition. This is a state in the Hilbert space. This curly H means the Hilbert space for me. So let this thing be the state of the system. And by this, I mean the state of the entire universe. So this state is supposed to describe every degrees of freedom, every occupation number of every particle in the standard model, as well as every particle beyond the standard model that exists in the laws of nature. Also, let's introduce a basis of field eigenstates, be a basis. I'm using the word basis a little loosely here. These are field eigenstates. What does it mean? It means that if you take a field at some time position x and time eta, and you hit this state, it gives back itself times a function, and that function depends on which state you hit. This is very similar to the position eigenstates of when you study quantum mechanics. There is a particle in one dimension. You have states that are called x, that are eigenstates of the position operator x. This is similar, but it's an eigenstate of the operator. So this is the set of eigenstates. Then the wave function is defined by the projection of that state on this basis. Okay, since sometimes it's hard to talk about vectors in a Hilbert space abstractly, we like to think about vectors in a given basis sometimes. And so since the basis depends on all possible functions phi of x, when you project it on this basis, it becomes a functional of those functions. So this functional is called the wave function. So it's just the projection of that arbitrary state at time eta onto this basis. Very good. So what was that arbitrary state? That arbitrary state was given by the time evolution operator u from some initial state, and the time evolution operator is e to the minus integral interaction Hamiltonian time from some initial state at time minus infinity. Good. Luckily for us, so we know this time evolution operator is what we know very well. This is exactly what evolved from one time to the other, and it is common to think and compute this instead of using the operator language of quantum mechanics using the path integral language. This is what we discussed last time at the end of the lecture. The whole quantum mechanics, both in quantum field theory and in quantum mechanics, you can say everything in terms of operators acting on a Hilbert space or in terms of path integrals. That's a completely equivalent description. It's convenient to use the path integral language here. And so in the using the path integral language, you might remember that the path integral was defined to be the transition from one state to the other, which is obtained by averaging over all possible trajectories, even the non-classical ones, even those that don't satisfy the equations of motion. So the path integral, or this, is given by the integral over all possible configurations of all the fields, weighted by some functional that is called the action of the system. And of course, this is an integral, so it needs to have some initial state. I'll just call it IC for initial condition. And it will end up on some final condition, which is that at some time eta, this field over which we integrate has to have a particular configuration phi of x. That phi is the same phi that we are talking about. So this will give a function of phi of x, which is a functional, is a functions of function. So what the wave function does for a living is that you give the wave function a function that tells you how the field is distributed, and the wave function tells you the complex probability to end evolution there from a quantum mechanical point of view. Okay, if this was an harmonic oscillator, you ask me what is the probability that I am here, given that I started from here, and the result is a complex number. Here is the same. Was the probability that I start with some initial state and I end with a final one. And in quantum mechanics, that's a complex number, or rather, this is the probability amplitude. And to get a physical classical probability, you take this and you do the mod square. That gives you a real number, which is the probability in quantum mechanics. Okay, how you can think about this is similar to what we said last time. There is some initial state in the past, and you're evolving it to some state at time eta, and you're using the time evolution operator from minus infinity to eta. This is like a rotation in an infinite dimensional Hilbert space. And then you are projecting it onto some set of coordinates that we are calling psi, and this is the result. Okay, that's so in some sense, you see, this is not so different from half of what a correlator is. The correlator is that you are going up, introducing an operator and coming back. Here you're just going up. Okay, it's kind of half of the correlator. This object is much closer to what an amplitude is in quantum field theory, in which you have some particles in and you ask what is the probability or the amplitude that some particles come out. This is in some sense the cosmological analog, except that it is phrased in terms of fields, expectation values, rather than particle numbers. So the way you should think about it is that the wave function is to correlators the same that amplitudes are to cross sections. In the sense that the real observables are correlators, as we discussed, or cross sections if you do particle physics. But the thing we like to compute as theorists is the square root of that, which is for particle physics and amplitude, and for us in cosmology here will be a wave function. Actually, the wave function can also be computed in flat space, so it's not unique to cosmology. However, in cosmology, it's very natural to compute because we do observe the system only at a certain time rather than seeing it at different times. So the wave function contains all the information about the system. Once I give you the wave function, you can compute whatever you want. from this wave function, which is a big beast. It's a big object. It's a function of all possible functions. And we can compute correlators. Using the Born rule. Okay, that's something that I'm sure you have encountered in quantum mechanics. The expectation value of an operator, if you know what the wave function is, well, let me give this, is just the average over all possible values of phi of the wave function operator wave function. We have a star here. Okay, so this is assuming psi is normalized. Otherwise, you simply divide by the norm. Great. So for example, okay, maybe I should pause. How do people feel about this wave function? Does this sound like a familiar object or a very obscure object? So I should spend more time discussing it. That's what I did last time. I was computing the correlators by evolving. Actually, I was doing it in the interaction picture, but that's similar, in which I was evolving the operators. Yeah, absolutely. And it will give the same result. However, in the Heisenberg picture, the wave function doesn't depend on time. Whatever it is at the beginning, it's that forever. So it's not very useful to compute. It's an initial condition. And where all the physics hides in the Heisenberg picture is in the time evolution of the operators. Well, in this picture, all the information hides in the time evolution of the wave function. And the wave function, because it only has one time evolution operator rather than two, is slightly easier to compute than correlators. And it still contains all the information. So the argument will be that this is a simpler object to look at. It's somewhat similar to the reason of why we compute amplitudes rather than cross-sections. Given an amplitude, we know how to compute a cross-section by taking the amplitude square and summing over the final set of states. But sometimes we just work at the level of amplitudes because they contain all the information and they are more interesting to work with theoretically. For example, they're complex numbers rather than real numbers. But yeah, this is completely equivalent to the Heisenberg picture. Yeah, excellent. Maybe any other question?
I have a question. In this case, is it possible to compute amplitudes by means of the correlators?
By applying an LSZ?
Yeah, I mean that.
Yes, it is possible, and it's something that has been proposed recently, either by myself and Yaniv Donat, as well as by two other people, Guy Pimentel and Scott Melville. So it's a recent proposal. There are several conceptual problems that make the interpretation of an amplitude in de Sitter space very confusing and subtle. In Minkowski, you can definitely do it. In Minkowski, you can just take the correlators and apply LSZ. In de Sitter, it's complicated. It depends exactly how you define particles and where you want to apply the LSZ. And there are several conceptual difficulties that I could describe, but that would take me in somewhat a different direction. But yes, people are exploring this possibility, and it is current literature. So there have been 2 or 3 papers just in the last year or so of people attempting to define this object.
Okay, I see. I have another question. Since we are dealing with wave functions, that is why we are using the path integral in this case, right?
Well, as I said, the path integral can compute anything you like. It can compute correlators if you bend it back. It can compute time order correlators if you make it go straight, but it can also compute the wave function. So I don't think it's correct to think that wave function means path integral. However, both the wave function and correlation function can be computed either using operators or using the path integral. So maybe there are 4 possibilities. You can compute correlators, wave function, using operators, or using the path integral, and all options are valid.
Yeah, but in this case, it's more convenient to use the path integral.
Yeah, I mean, I like it. So yes, I find it convenient, but it would be okay to do it in a different way.
Okay, I see. Thank you.
Yes, maybe you could just compute it instead of using the path integral, solving the Schrödinger equation. You can write the Schrödinger equation. This wave function satisfies Schrödinger equation. You specify what operator the Hamiltonian is, and then you start solving in perturbation theory. It gives exactly the same result. And you never say the word path integral. So that's completely equivalent. And there are some papers that do this. The path integral gives you a formal solution of the Schrödinger equation. And then by evaluating that solution in perturbation theory, it's another way of computing the solution. At the end is more or less the same effort.
There is another question on the chat.
Please, yeah, okay. I thought we were always using the interaction picture. How can I know what picture is used for quantum mechanics? Does it depend on the system or just on the theory itself? Neither. It doesn't depend on neither on the system nor on the theory. It only depends on you. So it's just a choice of how you prefer to organize the calculation. So for every system and for every theory, you can use any of the pictures of quantum mechanics, and they will all give the same result. They'll just organize the calculation in a slightly different way. And so in some sense, these pictures of quantum mechanics can be thought of to being equivalent to when you talk about active and passive transformation in classical physics. You can either change your coordinates or you can change your variables. The result is the same, it's just whether you take one perspective or another. So there is an object, which let's say for simplicity, we can call some operator and some state. And that object has just some value, which does not depend on how you compute it. You may choose to compute it in many different ways. And so the idea is that you want to know this object where you are, so Heisenberg picture, you're saying that A now changes in this way. And you're saying that omega doesn't change. And so what you're computing is omega. And this, now let's think of U as being the one that implements time evolution. So now you are computing the expectation value of A of t. Which is just the expectation of omega U dagger A U omega. The Schrödinger picture is computing exactly the same thing, but saying, now let's keep A fixed, and let's say that omega now depends on time. So now you're computing omega of t, A, omega of t, but that's exactly the same thing. It's just omega U dagger A, U, omega. And the interaction picture is doing again the same thing, but this interaction picture is also computing the same thing again in a third possible way. Interaction picture says, well, wait a second, U is going to be the time evolution of the free theory times the time evolution of the interaction theory. And now it's going to define some A interaction which evolves only with the free theory, and some omega interaction that only evolves with the interaction theory. But at the end, even in the interaction picture, we're all computing the same thing, the same as in the other two cases. We're computing omega, ui, u0, a, u0, ui, omega, where this is u dagger and this is u. So it's the same as all the others. So these pictures are just ways to organize your calculation. The Heisenberg picture is very useful when you do formal manipulations. And the reason why we like it so much is because it makes Lorentz invariance manifest. So for calculation in Minkowski is very useful. The Schrödinger picture is very intuitive because we think of the state as changing, like you are going shopping, rather than the observable shopping is moving towards you. No, that's a strange way of saying it, but we think of the system as evolving rather than the observable. That's what is explicit in the Schrödinger picture. And finally, the interaction picture is something that we like because we are not able to solve quantum field theories non-perturbatively. And we want to treat the free part of the theory fully non-perturbative, but the interaction part, we want to treat it in perturbation theory. So we want to split those two, and one we treat to all orders and the other not. And so splitting those two, then it's useful to use this interaction picture, where the free evolution of the operators is treated to all orders in perturbation theory, while the interactive part, that's the one that is approximated. So Enrique, to answer your question, it doesn't depend on the system or the theory, and can always do it for every system and every theory. Great, yeah. Any other question? Okay, no. So then maybe I'll go back to where we were, and we said, what is the wave function for a free theory? No, let me not tell you. Well, I'm going to compute it in a second, but I mentioned it last time, and I will prove it to you later on, that for a free theory, the wave function is always a Gaussian. Meaning for a free theory, I can always write this wave function as some normalization constant that I will drop, and the exponential of minus the integral over all possible k, some arbitrary function of k and t that I don't know, phi of k mod square. And I'm going to put a 1/2 normalization to this. So for every free theory, this is always the wave function, just e to the minus phi squared. Good. Then, from this Schrödinger picture, we can also compute correlators. Let's see. Let's compute the simplest correlator. Let's compute the power spectrum. So as I told you, the power spectrum is the expectation value of k squared. Let me compute it at equal time. Let me specify that the wave function is very good to compute equal time correlators. So maybe I should say that. I will not write time, but everything is evaluated at the same time. So you should use this Born rule that says do an average over all possible phis of the wave function squared times phi of k, phi of minus k. Sorry, phi of k prime. Okay, so now what happens? If k is different from k prime, then I'm doing a Gaussian e to the minus phi squared times phi. But the average of phi for a Gaussian is always 0, because in the Gaussian it is half of the time is positive, half of the time is negative. So that's going to be 0. This thing is not going to be 0 only when phi of k and phi of k prime are the same. Then I'm squaring that, and that's not 0. So there is always going to be a delta function. And my convention on the delta function is that it comes with a 2 pi cube. This is the same delta function of momentum conservation times the Gaussian. Now it's just the 2-point function. The 2-point function, you know, is just 1 over the coefficient of the Gaussian, right? This is like every Gaussian integral. The 2-point function is 1 over that. And the factor of 1/2 is correct. Since the wave function, you take the mod square, you only care about the real part of psi2. The imaginary part disappears when you take the mod square. Okay. So the power spectrum. Okay, so that's the power spectrum. I mean, I haven't computed explicitly because I didn't tell you what. So this thing is what we were calling the power spectrum. In a second, I will compute for you psi2, and then you will see that it gives us the same result as the power spectrum that we computed. And if I got my conventions right, my conventions is that this is a plus. And the result is -1. Okay, this is my convention. And you can see that if the Gaussian is actually coming down, then this power spectrum is always positive. So when the wave function is normalizable, it gives me a positive power spectrum, which is what it should be, because the power spectrum is the expectation value of something squared. Okay, let's compute this wave function and therefore this psi2 for the free theory. So something that it took me many years to appreciate is that a lot of physics is mostly about free theories. So it's really good to understand those free theories as well as you can. Okay, so a free theory has a Lagrangian which is quadratic in perturbations. Then we can perform the path integral that defines the wave function. Remember, the wave function was defined by this path integral. But if this exponential is just quadratic, this is just a Gaussian path integral, and I know how to perform it. And so I'll sketch for you the calculation. In particular, you might know this, or maybe not, that the path integral of a Gaussian distribution is proportional to the stationary, is exactly proportional to the stationary phase approximation. In fact, the stationary phase, where you approximate the path integral by asking when the phase is satisfies is stationary, so the derivative of that is 0, that is not an approximation for a Gaussian path integral, is exactly the right result. And when the theory is non-Gaussian, then that is just an approximation that we call the semi-classic approximation. That's how classical physics emerges from quantum mechanics. But if we talk about free theory, this approximation is actually exact. So the path integral is exactly given well, when I say exactly, I should say is given up to an irrelevant normalization factor. Because we don't care about the normalization because we always normalize the wave function by the stationary phase, which is not an approximation. Here is exact. So psi for a free theory which in principle would be a complicated path integral, who knows what it is just given by evaluating e to the is on the stationary phase. And the stationary phase, I'm going to call it phi classical, because phi classical is the solution of the classical equations of motion. So this is exactly equal to this times a normalization that does not depend on the field. So just a number, you can normalize it out. Phi classical is a function of space and time, which is the solution of the classical equations of motion. Okay, meaning, okay, the classical equation of motion are just box minus m squared phi equals 0. With boundary conditions, let's see, what are the boundary conditions? We want to start from this Bunch-Davies state and end up with this configuration phi. So the correct boundary conditions are for phi classical at time, let's say that we computed the wave function at time eta 0. At time eta 0, this function should be the function that appears in the variable of the wave function. This phi here should be this one. Okay, we're asking all of the configuration that end on that particular phi of x or phi of k in Fourier space. And the opposite, the other boundary condition, I'm giving it at minus infinity. And the condition is that if eta goes to minus infinity 1 minus, or I think actually is correct, this time is 1 plus I epsilon, then this thing vanishes. So this is what imposes the Bunch-Davies initial state. And I could prove to you that this I epsilon is the one that projects on this state, but I will not do it. Okay, we know what the solution of the equations of motion is what we're calling the mode functions. They were defined to be the solution of the classical as equation of motion. Then with this boundary condition, phi classical is nothing but f, which was the mode function that solves the equation of motion, up to some normalization. The normalization is such that when I evaluate this at eta equal eta 0, this gives me phi of k. Boom, I found what phi of k is. And now, if I want to compute the wave function, I should shove this into the action, into the IV action, and that should be the result. So instead of computing psi, let me compute log psi, so I don't have to write the exponential every time. This is just I as evaluated on phi classical. Okay, what is the action? For a free scalar field, the action is the integral in d3k, integral in d eta, square root of g, which gives me a to the minus 4, 1/2 d mu phi classical square. Okay, in principle, I can just take the function phi classical inside this and see what it gives. It's quicker to do the calculation if we notice that we can integrate this thing by part, and we can write it as the equations of motion plus I over 2, sorry, plus 1/2, the total derivative. Okay, here I'm using nothing but the fact that if you take this derivative by part, the result of that integration by part is precisely the equations of motion. But phi classical was defined to solve the equation of motion, so this term is necessarily 0. So it's the waste of time to compute it. We know it's going to be 0. And so the only thing that survives is that boundary term in this action, in this classical action. And so the result is I over 2, the integral in dk. Now, this is an integral of a total derivative. In space, the boundary condition is that all field configuration should vanish at spatial infinity. That's the standard conditions that we have in quantum field theory. So all the boundary conditions in space, we can throw them out. But the boundary condition in time, we cannot throw them out because phi does not vanish at the time boundary of this integral. So the result of this is that we get phi classical when you put the a to the fourth, the inverse metric, the time derivative of phi classical, and it all should be evaluated at the two boundary of the integral, minus infinity 1 plus I epsilon and 0. At minus infinity, we just put the boundary condition that the wave function vanishes, that the solution vanishes. So that we can drop. And so the solution is just 1/2 integral in dk phi of k, phi of minus k, psi2, some function, which I called psi2 before, where now I know what psi2 is because I just computed it. Psi2 is I. Okay, so now what I'm doing is that I take this one was the mode function at the boundary. This is just phi. This is the other mode function. I take the derivative of it, and then I evaluate it at the boundary. That gives me phi times a function, and I write the function here. And I spare you the detail. The function is simply minus k cubed divided by 1 plus k squared eta squared plus I k squared one. Good, that was the result. So that's great. So we computed our first wave function for a free theory. Good. So is the wave function, does it look good? Yes. So first of all, you see this minus sign here is crucial. It means that psi goes like e to the minus phi squared, and so it's normalizable. Like a harmonic oscillator. If it went like phi e to the plus phi squared, that would be a problem. This one, this is an oscillating phase. It's a divergent phase. When I send eta to 0, but it disappears when you compute psi squared because it's just a phase. Okay, this result is exact. No approximation, no perturbation theory. And of course, this agrees with the power spectrum calculation. Let's see if it agrees. So I told you to compute the power spectrum, we computed it when we send eta 0 to 0. And if we only care about the real part of this, this is I over h squared minus k cubed over 1 plus 0. This is just I k cubed over h squared. And indeed, we had written that the formula for the power spectrum is minus 1 over twice the real part of psi. Sorry, this is not an I, this is a 1. And if I take the inverse of this is 2, sorry. The inverse of this is 2k cubed divided by h squared, which is exactly what I had computed the last time. So I found that indeed it gives the same result as it should, but I computed it in a very different way. Okay. Any questions so far?
I have a question. In order to deal with that divergent term, is it necessary to write a counter term?
Yes. So formally, you can write down a counter term. That reabsorbs it. And because this term is, you can see it's analytic, it's just k squared. Actually, it's just the kinetic term provides that counter term. And you can reabsorb that divergence if you want. This has been studied quite a bit in ADS CFT. It goes under the name of holographic renormalization because it takes although this is a calculation that I'm doing at finite time, in ADS, this is a calculation that you do in the bulk of ADS, and in the boundary, it takes exactly the form of the renormalization group flow of the dual conformal field theory. In the sitter, it's slightly different. If you try to reabsorb this with a counter term, you need to put imaginary counter terms, which appear to break unitarity, although once you cancel them out, they're just gone. But yes, you can reabsorb this with a counter term. There is a similar term that would appear if you computed the two-point function of the graviton, of the wave function, if you want, of the graviton, and that would also be reabsorbed by an imaginary corrections to the Newton constant. So yes, a counter term will absorb this.
Okay, I have another question. At the moment, are there renormalization schemes for cosmological correlators, or can be the same as in the in-out formalism?
Yeah, I think I mentioned something last time, but I can say it again. So far, we're just doing free theories, so no need to renormalize or regularize. For interacting theory, yes, people have studied some renormalization. They have studied dimensional regulation and cutoff regulation, renormalization, I mean. And they are subtle, and there are papers on it, including several by myself. And I can give you some references. What's subtle is different renormalization do different things to scale invariance, and then you have to decide which one is the correct way of doing it. So I think it's much more subtle than flat space, where everything you do gives the same result, at least at one loop, for example, for the beta function. While in the sitter, things seems to be more subtle. But yes, it's understood how to do it, I would say. At least it's understood that there is one prescription that gives a result that seems physically correct. But much more study would be needed to understand this better.
Okay, I see.
Okay, is this a good time to take a break, maybe? Okay, good. So let's talk about the wave function for an interacting theory. So for interacting theory, the wave function is not a Gaussian. It could be, in principle, a very complicated function. we're going to assume that no matter how complicated it is, we can write it as the exponential of an infinite sum, 1 over n factorial, sum from n from 2 to infinity, of psi n, phi of k1, phi of kn, times, and this is an integral, in k1 kn times a delta function of the sum of k's. So this is similar to the wave function of a Gaussian theory, except that now instead of just putting n equals 2 psi 2 phi squared, I allowed psi n to any n. In other words, you can think if you take the log of psi, I just Taylor expanded the log of psi around the minimum, saying that it's phi squared, phi cubed, phi to the fourth, etc. So this is a sufficiently generic parameterization for most calculations in perturbation theory. Of course, I don't know what these psi n coefficients are. So those are the ones that I will want to compute given for any given theory. This psi n coefficient, in principle, they depend on the momenta, k1, k2, kn, and also they can depend on time. That's where the time dependence of the wave function is hiding, and they are called wave function coefficients. Okay, given this, we can compute also non-Gaussian correlators. So if you have an interacting theory, then the wave function is going to be not Gaussian, but you can still use exactly the same formula to compute correlators. So for example, the correlator of Ka to the power n products of this will again be given by this boundary average over all possible values of phi of the wave function operators wave function. And this can be performed in perturbation theory. And it gives, so if I evaluate this expression in perturbation theory, I have e to the minus 2 integral real part of psi 2 pi mod square from the Gaussian part of the wave function. And then the non-Gaussian part, I expand it. I will have 1 plus integral of psi 3 phi cube plus integral of psi 4 pi to the fourth plus dot dot dot. And this will appear as the norm square of this, because it's the norm square of the wave function. And then I will still have the product of the field whose correlation function I'm computing. Now you can see this is, again, it's a Gaussian integral. So it's a Gaussian integral of phi to many different powers. And we know how to perform all those Gaussian integrals of phi to any powers. Just a standard formula of Gaussian integrals. In some sense here, you can see that this can be performed by doing Wick contractions and writing phi to the n as the 2-point function to the appropriate power. So just to give you a concrete example, For the 3-point function, this gives I'm going to put a prime to drop the delta function. This gives just psi3 of k1, k2, k3 plus well, let me write 2 times the real part of this divided by the product over A of 2 times the real part of psi2, just because every time I do a Gaussian integral, I get 1 over the 2-point function, and the psi3 is just what came out from to lowest order. In taking this square, it is this times this, which is psi3 phi cube, and then the other one is psi3 star phi cube. That's twice the real part of times phi cube, and here there are another 3 phi's, so there are 6 phi's, so that's 3 pairs. So 3 pairs means I get 3 powers of the 2-point function downstairs, and then I get twice the real part of psi3. So that's the final result, plus of course higher orders, which I write as HO. I should mention that all of these lectures are based on some notes that typed up notes with all formulas and details and factor of 2. So if you're curious of the details, or if you want to do some work on this, you can also check out the notes. I shared them with Daniel. So I'll refer you to the notes for more examples. Okay, good. So the last thing that I wanted to tell you in these lectures was, well, the last 2 things, in fact. One is that I wanted to tell you 2 words about how to compute the wave function for interacting theories. And so there are some Feynman rules. So I call them wave function Feynman rules. Diagrammatic rules, maybe. And so these are similar in spirit, but it's different in detail from the rules that we use to compute correlators. And these rules, what they do, they compute psi n. If you apply these rules, you can compute psi n. Like before, you can derive these rules either from the path integral definition of the wave function or from the operator formalism, and they give the same result, the same Feynman rules. I will not derive them from you, but I'll tell you the rules. So the first rule, as always, is you draw. These lines represent time. For us, time will be eta 0, which I'll set to 0 sometimes. So that line just represent that I'm computing this wave function at some time. And then the rules is that you draw the same number of external legs as the number n of the wave function that you're computing. If you're computing psi3, there are 3 external legs. Psi10, there are 10 external legs. And you label all the external line with a 3 momentum going from k1 to kn. And there are vertices and there are propagators. So again, like before, time runs up. Eta equals minus infinity is in the past, and eta equals 0 is in the top. Then there are 2 types of propagators. There are bulk boundary propagators. Bulk means that you're below this line, and boundary, it means that you're sitting on this line at eta equals 0. Is a language that has been borrowed from ADS CFT, but nothing to do with CFT. Propagator. So this is the bulk boundary propagator. This is another bulk boundary. These are other bulk boundaries, all the lines that are going up. And then the other line are going to be called bulk propagators. I'll show them to you in a second. So for a bulk boundary propagator is a line that goes from some time eta to the time eta 0. This is a propagator that I call G eta. Oh, sorry, no. This is a propagator that I call K of eta, and is equal to F star of eta divided by F star of eta 0, where remember, this of course also depends on momentum, and it's called with capital K. And this satisfies the equation of motion because it's just proportional to the mode function, and the boundary condition is that it is 1 at the boundary. And there is also a bulk propagator. That's given by a different function. This is called G. There is only one because there are only one type of vertices in this game. Eta 1, eta 2. This is equal to the power spectrum times the bulk boundary star of eta 1, bulk boundary of eta 2, times a theta function of eta 1 minus eta 2, plus 1 exchange with 2, plus, rather minus, k of eta 1, k of eta 2. Okay, what is this thing? The first part of this is familiar to all of us and is nothing but the Feynman propagator, the time order 2-point function. That's to be expected because remember, we are computing the expectation value of a state, time evolved by some amount of time to another with e to the time order of e to the I h. Since it's inside the time order, there should be a Feynman propagator. Well, this other term here is called the boundary term. And that's responsible for ensuring that this propagator vanishes when either of the time is taken to the boundary. Notice that this propagator is symmetric. Like the Feynman propagator. Good. Then the other thing that you need to know when you have these diagrams is that every vertex, what do? Vertices I need to integrate at all possible time, at all possible space, because these are interactions, but in quantum mechanics, interaction can happen at all possible times and space, so you have to average over all of them. And so the average over space just gives you a delta function, so momentum is conserved. 3 momentum is conserved. Notice this is different from the Feynman rules for amplitudes where 4 momentum is conserved. So energy is also conserved in Minkowski, but not in general cosmological space-time. Only 3 momentum is conserved because space is homogeneous, so invariant under translation, and that leads to the conservation of momentum, but is not invariant under time translation, so there is no conservation of energy. Instead, for energy, you actually have to perform the time integral and see what comes out. It's not automatically a delta function. And the integral is the usual minus I lambda integral in the eta of square root of g, which is a to the 4th in FLRW space-time times some interaction vertex. The interaction will depend on the theory that you are considering. I wanted to give you one example. And you will see that it is very similar to the calculation we did before, but slightly simpler. For example, let's consider the interaction Hamiltonian to be n over n factorial phi to the n in Minkowski. That's the same example for which we computed the correlator. Then psi n is just given by this diagram. So here I have to write I lambda Yeah, okay. Let me say that, yeah. Minus I lambda interaction in dt. There are only bulk boundary propagators. There is n of them, and each one is k. And there's one for every different external momentum. So minus I lambda. This is the integral from minus infinity to 0 in dt. All of these propagators are very simple because if we are in Minkowski, remember the mode functions f is just e to the minus e to the plus I omega t, and you divide by e to the 0, which is 1. So this is just e to the I omega t. And when you multiply n of them together is e to the I total energy times time, where I remind you that E total is just the sum of all the energies of each individual particles. Okay, this integral is very simple. It just gives you minus I lambda 1 over I et evaluated from minus infinity, 1 plus I epsilon and 0. The lower part of the boundary just gives me 0, and the upper part, oh sorry, there is the exponential, of course. And the upper part just give me 1 over I et. The I cancels. And so the result is minus lambda over E total. The n factorial also canceled. Great. Okay, note that the residue of E total equals 0 is the Minkowski amplitude. A fact that generates a deep connection between the wave function and amplitude, which has been developed a lot in the past few years. And I have another example for the sitter, but I will skip it. Okay, good. So are there any questions about this? No. Okay. Good. Then I'll conclude these lectures with just a few comments on phenomenology, and maybe I'll say a few words about what people are doing, but I will not discuss it in detail, any recent result. Okay, so the primordial two-point function, the power spectrum, has been measured. So the two-point function has been measured. This is the two-point function of zeta. Zeta of k, zeta of minus k. Remember, this is a delta function that I dropped. This is some amplitude divided by k cube, and the amplitude has been measured to be of order of 10 to the minus 9, so much smaller than 1. Okay, so primordial perturbations meaning how much our universe is different from a perfectly homogeneous and isotropic universe at the very early on, are small. So it means the universe was very close to being exactly the same everywhere in all directions. Maybe I remind you that zeta is the thing that appears in the deviation from perfect homogeneity and isotropy of the space-time metric. Because this zeta is so small, if you're trying to compute a correlator with many zeta, like zeta cubed, zeta to the 4th, zeta to the 5th, it's very small because you're multiplying times 10 to the minus 5 every time. So the fewer zetas you have, the easier it is to measure. So people are looking for mostly the 3-point function, the correlator of zeta cube. So most cosmological surveys target n equals 3, which is the 3-point function, which cosmologists call the bispectrum, which is a very confusing word, but that's what they call it. Okay, so let me see what the bispectrum is. This is the 3-point function of zeta at the beginning of the hot Big Bang or at the end of inflation. This again has a delta function, like always, of momentum conservation. And it also has a 3-point function that depends on what these momenta are, K1, K2, and K3. Because these momenta have to, as vectors, have to close to form a triangle, then I can specify any triangle by just giving the length of the vectors rather than this is K1 vector, this is K2 vector, this is K3 vector. They have to close a triangle because there is a delta function. So usually this is parameterized as having a shape and a size. So B3 is written as an overall size that is called F and L, and L stands for nonlinear. This tells you how big this correlation is. This is the overall size. But then it might depend on K1, K2, K3. So by convention, usually this is multiplied times the square of the power spectrum. And then what's left depends on only the ratios of K2 over K1 and the ratios of K3 over K1. And that's called the shape of the power spectrum. So is this correlation bigger when I deform the triangle? For what triangles is this correlation biggest, and for what triangles is it smaller? And people have looked for this for now more than 20 years, and it has not been detected. The strongest bound comes from the best measurement of the cosmic microwave background by the Planck satellite launched by the European Space Agency. And they give bounds that this nonlinear parameter is smaller than of order 10. That's not the bound. Actually, they don't say if it is positive or negative, so it's just the bounds on the norm of this. Of course, yeah. Okay, are these strong? Okay, yes, and the strongest bound, they come from taking the expectation value of the cube of the CMB temperature or the CMB polarization, or a mix of them? Good. Is this a good bound or a bad bound? It's actually an excellent bound. Let's see, how Gaussian is this? Well, let's try. Let's take psi. Remember that the definition of the wave function was that this thing was e to the minus psi 2 square phi square plus psi 3 phi cube plus dot dot dot. And then psi 3 was related to the bispectrum schematically by B3 was psi 3 over psi 2 cube. Therefore, we can write psi 3 as B3 times psi 2 cube. But this is the same as FNL power spectrum square shape divided by power spectrum cube. So this is equal to FNL times psi 2 at the end of the calculation. Because power spectrum, remember, is 1 over psi 2. Hence, we continue our estimate that, therefore, psi, if it was a perfect Gaussian, the log psi would just be psi 2. Oh, sorry, this phi, oops. I should call this zeta, right? Because we're talking about the field zeta. This would be a perfect Gaussian, but in principle, it could be different from a Gaussian, and different is FNL times zeta itself. So this would be the amount of non-Gaussianity, meaning deviation from it being a free theory. And current bound, what does it mean? It means that FNL times zeta, where I estimate zeta to be the square root of the power spectrum. Well, this is, I know that square root of the power spectrum is approximately 10 to the minus 5, and this is smaller than 10 times 10 to the minus 5, which is 10 to the minus 4. So the deviation from a Gaussian is smaller than 10 to the minus 4. So our universe started with extremely Gaussian perturbations, which is a remarkable fact that deserves an explanation. And in fact, maybe I'll conclude with the statement that Gaussianity is the most precise constraints that we have on the early universe. Good. Okay. Well done. I think that was everything I wanted to say. So yeah, thanks a lot for listening. If you have any questions, I'm happy to stay here for a few minutes to answer them on anything I said or anything I didn't say, or if you have other curiosity, I can try to do my best to answer it.